Hi everyone. Today we'll discuss something here in connection with the class relations. So we'll see that the class relation come into play for these subjects. I think I will mainly concentrate on well-ordering principle, but of course we'll mention mathematical induction, which you have learned in high school, I believe. Okay. Of course, for these two important ideas or proof techniques, we need natural numbers. Natural numbers. So perhaps everyone knows what natural numbers are, right? Okay. We'll see. Okay. All right. So let's assume that everyone knows very well what natural numbers are. And based on this, we'll discuss well-ordering principles and the mathematical induction base. This will mainly after the holidays, I think next week. But I will mention some, okay? In connection with the class relations. Actually, the class relation play very important role when we use these two things, okay? I thought it sounds right. All right, so let me start with this very, very simple idea, and it looks to be very, very obvious. So that's why it's called axiom, well-ordering principle. Maybe, okay, maybe don't like this word because we can depend. Okay, we can use induction to prove this one. Okay, well-ordering principle says for any non-empty set of natural numbers, we always have a smallest element. Okay, so every non-empty set, or you can say subset, same thing. Okay, every non-empty set or subset of natural numbers contain a smallest number. That's pretty obvious, right? But actually, it's not as obvious as you may think. Consider different situation. Instead of all natural numbers, suppose we talk about real numbers. So it's kind of sharp, this theorem. So if we talk about real numbers, so in place of natural number, we replace it by real numbers, by reals. Since this one does not hold, see, I can give you a set of real numbers that have no minimum element. For example, we consider all real numbers, say from 0 to 1. So maybe it's a bigger. Consider all real numbers in the interval from 0 to 1. Of course, it's a set of real numbers. Okay, so in place this one, we use this one. Of course, for this particular set, 0 is minimum element. Now, if I take away 0, the interval this side is open. Since the set has no minimum element, so you can choose maybe 0, 0, 0, 0, 0, 0, like 1. This is close enough. But it's not minimum element. 0, 1 is smaller than this one, and so on. So this one does not have a minimum element. All right, so this one is kind of sharp. Actually, even for rational numbers, we have same situation. Oh, sorry. Yeah. So even positive rational numbers. So instead of natural number, we replace it by positive rationals. Again, the set may not have a minimum element. Again, well, we can use this one as example. Again, consider numbers between 0 and 1. Consider numbers in this interval. So consider all rational numbers, all rationals. In this interval, of course, we have smallest element because of 0. Now, again, if I take 0 away, I have a non-empty set of rational numbers, but then we don't have a minimum element. You can give me one that's very, very small, maybe this small. But I can find another one that's even smaller. It's also in this set, and so on. I can never find the one that is minimum, even for rational numbers. So this, in this sense, this one is not obvious. But we cannot prove it. How can we prove it? So that's why it's called axiom. But if we use other things as axioms, then we will be able to prove it. For example, mathematical induction, then we are able to prove this one. Okay. All right. So anyways, it's a very, very simple property about integers. However, it's quite useful to prove things. So remember, this part needs to be natural numbers, otherwise it does not hold. So we'll be able to use this very trivial property to prove interesting things. So the way we do it is as follows. Suppose we want to prove that Pn, a statement, Pn, a predicate, holds, or proposition holds for all integers. Okay. Suppose we want to prove a statement, Pn holds for all natural numbers. All right. For example, I give you an example. This one will go to the other one. It's n plus 1 square. Then it's become n plus 1 square. Maybe it's easier to write from 0 to 1. N squared. Okay. So otherwise, it's different by 1. It's 0 to n, it's n plus 1. Suppose we want to show that the sum of first n order numbers equal n squared. We want to prove it. So this Pn, statement Pn. So in this case, this is a statement we want to prove. Of course, we know in high school we can use mathematical induction to prove it. I'll come back to that one in a minute. Okay. Another way to prove it is to prove this statement by contradiction. Another way is prove by contradiction. So how do we do that? So assume this one does not hold. So assume that this is not true. So that means there exists an n such that Pn is false. Sorry, this one, sorry. Exists an n such that not Pn. All right. So suppose that's the case, then we want to obtain a contradiction. So what we want to do is from this assumption, suppose there exists an n such that Pn does not hold, then logically we can induce that there is contradiction. So therefore something must be wrong. If we logically obtain results from this assumption, everything is right, so the assumption must be wrong. All right. So we can use this idea and use well-ordering principle to prove things. So here, this one is called a counterexample. For instance, the statement does not hold. So this one is called a counterexample. So what we do is assume there are a counterexample. Then we'll be able to obtain a contradiction. All right. So that's the idea we're going to use. All right. Okay, suppose there are a counterexample to this one. Now we can construct a set. We can construct a set of natural numbers where for each k, pk is false. So that's a set of counterexamples. We use the index. Okay, so that's the set of index, of set of indices for counterexamples. So we can form a set. All right. Now, original statement, this one is true. Is true if only if this one is empty. So original statement is true if only if this set is empty. Otherwise, if this set is not empty, then this will not true. All right. So that's the idea behind it. So suppose this one is not true. This one is not true. Then we will have a non-empty set. Now here, where ordering principle come into play. Well, once we have this set, we know that suppose Pn, suppose under assumption that this one does not hold. This one false means C not empty. So that's our assumption. We're proving it by contradiction. Okay. So this one is not empty. Now, by well-ordering principle, C contains there are minimum number in C. Okay. Okay, we know among all these K's, there are the ones that is our minimum value. Okay, so what does this tell us? This tells us So we know that Pn and Pk star is false. So this one, we're ordering principle tells us two things. One is Pk star is false because it's in the K star is in this set, right? Second, because K star is minimum one. So we know that Pn is true whenever n is less than K star. So that's what we can infer from this result. All right. Now, once we have that, we are going to get a contradiction by following. So the way to get a contradiction. All right, so how we do it? Here are the load map. There are two ways. One is, so basically we use this one. Now you should be able to see the connection with induction, mathematical induction. So what we are going to do is use this one. So either, so from here, okay. Using this result, we try to prove that Pk star actually is true. Do you see? Actually, the thing we are doing actually is the idea behind mathematical induction. We assume the statement holds for every integer less than equal to less than K star, then we show it also holds for Pk star. So that's what we do when we use mathematical induction. But here, actually, this idea is very, very similar to mathematical induction. In mathematical induction, this one would be induction hypothesis. So we use induction to infer that this one holds. All right. But here, actually, we are doing, the point of view is different. Here, we go to its contrapositive. In order to prove this one, if this one is false, then this one would be false. All right. So what we are doing when this one choose, this one choose, so that's a contradiction. So that's showing the same thing, but rather the point of view is different. Here it's more from its the contrapositive of induction statement. From this one we prove this one is true. But actually here, what we are doing is when this one is false, we show this one is false. Now in order to do this, again, we use it contrapositive. That's what we do in induction. But the thing, what we are really proving is whenever this one is false, if this one is false, then it cannot be the case. All right. Okay. So that's one way. It's very much like mathematical induction. Under this assumption, actually we get a contradiction. So this one is true, so it contradicts to this one. So it cannot be the case that everyone holds. Okay. Another way is just as we did it here. It's another way is again from this one. Another way is we find a small k, smaller number k prime, so which is less than k star, but for which pk star is also false. So that contradicts to k star is the minimum element. So there are two ways. One is to do like this, another way to do things like this. I will give you two examples to illustrate these two. All right. So get a rough idea. These two examples should make things more clear. All right. Okay, so that's the idea behind the well-ordering principle. The idea is the principle itself is very trivial. So trivial thing, basically, we cannot prove it. It's an axiom. Okay. However, it's very simple, but it's very, very powerful. Okay. So first example is this one. Let me see. There are some. Oh, it's anything special? Oh, no sound. Once you said no sound, but maybe because okay. So maybe not my problem. Okay. All right. So first one is this one. So we want to prove this statement for all integers, for all natural numbers. So suppose it's Tn. So suppose this is not true, and the other smallest k star. All right. Okay, so this one is a counterexample. Suppose there is k smallest. Okay. Now we consider p. So we know. So what we know? So pk. So that's the meaning of this one. So pk star does not hold, but pk for all k less than k star. All right. So now let's consider this. Do summation up to k star. All right. So we don't know whether it's k star squared. Okay, we have no idea. Okay, so let's see. That's what we get. All right. Now, of course, this one equal k star minus 1 equals this one. All right. Now, you can compare with induction, mathematical induction. Actually, the same thing, same idea we use here. So, if we use mathematical induction, we apply induction hypothesis to this part. But here we use this one. By property of k star, we use this one. If we were using mathematical induction, this one would be called an induction hypothesis in mathematical induction. All right. Here we don't call it in this way because this one is not induction hypothesis. We are not using induction. Rather, by the property of k star, we have this property. All right. So it's not called a mathematical induction or induction hypothesis here. All right. But we have this one. So therefore, this one means equals this one. This property gives us this one. All right. Now when we add these two together, of course, we get k star squared. So what we get, now we know that pk holds, pk star holds. So the inequality holds from k star as well, but this contradicts to our assumption it contains a counterexample. So this one means this one is not counterexample. Therefore, there's a contradiction. Because everything follows from this assumption. So therefore, the assumption must be wrong. So therefore, this one does not hold. So there is no counterexample. So eventually means this one holds for every n. This one holds. So this one is true. All right. So we use very simple idea. Suppose counterexample exists, then we get a contradiction to the assumption that the counterexample exists. So we assume count example exists. So PK star does not hold. K star is a count example, but eventually get contradiction to this assumption. All right. Okay. So that's one example. Next example, we try to prove square root of 2 is a irrational number. We discussed one proof already in the first week. So here we will discuss a different proof. The proof will be based on well-ordering principle. All right, so we want to prove the square root of 2 . All right, now it seems nothing to do with the well-ordering principle at all. If you look at this one, it's just a particular number, nothing to do with n. But that somehow will establish a relation between this problem or this statement with well-ordering principle and use the well-ordering principle to prove that indeed square root of 2 is irrational. All right, of course, it's not trivial. It's simple, but it's not trivial. It's not easy to come with that proof by yourself. For the previous example, it's easy to come with that proof. But for this one, it's not that easy. So it's not difficult at all. Once I tell you, it's not easy, not difficult to understand. All right. So what we do is as follows. So this number is irrational. So suppose not the case, then we'll get something, some contradiction. So suppose this number is rational. Maybe I should say. Okay, so what we're going to prove is prove by contradiction. So suppose square root of 2 is rational, then we try to get a contradiction. Okay, so this is our assumption. Eventually, we want to refute this assumption. So this one is false. So therefore, square root of 2 is irrational. All right. So how can we do it? All right. So from this one, first we note that if this one is rational, it's a rational number, then square root of 2 minus 1 is also rational. Of course, it looks strange why we do this, square root of 2 minus 1. Okay, so you will see, because in the proof, this one will be very useful, this particular number. All right. Now, because this number is a rational number, if we multiply it by some integers k, so k is a natural number. Consider this number, multiply this number by k. For example, I give you a rational number, I say maybe 3 over 5. When I multiply it by integers, this number, consider this number, for some integers that become an integer, some may be still, it's not an integer, okay? So for example, for k equal, let's maybe list it. So k equal 1, 2, 3, 4, 5, okay? So we'll see that if k equal 5, this number becomes 3. But for all these, it's still fractional number. For k equal 5, it's 3. For 10, equals 6. So for some, it may become an integer. All right? Okay? So once you see that, we'll construct a set. So we construct a set. Construct a set. Okay. So let's give it name maybe A. I don't know. Just give it name A. All right. Now we have set of integers. Originally we deal with one number, so it's just nothing to be related to where ordering principle. Now we construct a set. Now this set, it's a set of integers. It's a set of integers. All right. So it contains all natural number k such that this number becomes an integer. And it's not empty. This set is not empty. All right. Okay. Now by well ordering principle, okay. Here maybe it's easier maybe to even assume this one is to exclude zero, maybe better. Okay, but it should also work, I think, even with zero. If we want to exclude the zero, maybe I write as Z star here, Z plus. So K is not zero. Yeah, I don't think it's necessary, but anyway, positive integers, okay? Since there are smaller integers inside the K, inside this set, all right? Maybe I use bigger K, maybe, because K is called maybe big K is better. Okay. All right, sensor watch. So here I will use the second load in the load map. I try to get a number smaller than K star inside the K. Now I didn't have a set. Now I try to get a smaller set. So I try to argue that exists some K prime less than K star, such that K prime is also inside the K. So that's the approach I'm going to take. Because here, look, here assuming K is smallest now. Now what I want to do is find the smaller one, smaller than K star, and it's also in this set. Of course, that's called a contradiction. Because this contradiction, that means this set must be empty. Because if not empty, if you think this one small one, I can always find a small one. You give me one, I find a smaller one. So you give me consist here, so you give me the smallest. So that means there's nothing here. But now what I do, I will find one is smaller than you. So there's a contradiction because we assume everything should be on this side, not on this side. Okay? All right, so how can I find a smaller one? Let me see, I use notation PQ here. I remember you notation PQ. Instead of case, okay. It may notation may be different from the notes. Okay. So I use case style. Okay, I will not use PQ as in the notes. So what we know is this one is a positive integer. This one. All right, and K is smallest. That's what we know. All right, now I consider this number. I want to find a smaller number. All right, so what I do is consider K prime equals square root of 1 minus 1 times this number. So I consider this number, set this K prime equals this number. Now this number is smaller than K star because this one is less than 1. Square root, this one is roughly 1. Say smaller than is okay. So I just say less than, okay. All right. So this one is smaller than 1. When this one times this one, of course, is less than k star. So it's here. All right. Now I want to show that actually in this number, also in this form. And look, it's very similar already. It's here square root of 2 minus 1 times this part. So it's indeed in this form, but what we need to show is this one is integer. All right, now I want to show this whole number is integer, and it's of this form. Now this one is of this form. It's square root of 2 minus 1 times integer here. We know this one is integer. So integer times this one. So it's in this form. Now I want to show the whole number is also integer. If it's integer, so that means this k prime belongs to the set k. So indeed it's here, but it's also in the set k. But that will cause a contradiction because we know this one is smallest. Now this one is smaller. Okay. So what remains to show is this whole number is integer. So why is this the case? Okay, so what we need to do is show two things. So that's our objective, to show that k prime is also belongs to a set. Set will cause contradiction to k star is smallest. Okay. Now, in order to show this, we want to show two things. One is k prime is integer. Say positive. Okay. Secondly, it has this form. Times something. Let's see. Oh, okay. Hold on. Some notation is not good. No, some notation is not good. Let me change it. Okay. Let me change it. Okay. Some notation. Not actually k star is here. This one is k prime. This one is k prime. Let's see. So I should not use this notation. Hold on. Here I don't use. Let's see. I use k. Use a different name. Okay. I use this one already. Maybe just use x. Okay. Just use x. So actually, want to show this one is k prime. That will be k prime. Fine. Yeah, okay, so I missed that with the notation. Okay, just use x to denote the whole thing. So I want to show this one is k prime. So I want to go is this k prime belong to this set k. So initially this k, you see it's of this form, square root of 2 minus 1 times something. So that's k star. Here square root of 2 minus 1 times this number. Okay. Okay, so I don't need this one actually. Okay. Now, in order to show that this one says this k prime times this one equal x, this x needs to be an integer in order for this k prime to belong to k. So we need to show that x is an integer. Okay. Okay, so this one by this assumption is there already, no need. Okay. So what we need to show is this product give us a number. We need to show this number is an integer. So therefore this one equals square root of 2 minus 1 k squared. This one number will be inside the k. Okay. So what remains is to show this number is an integer. Okay. Of course, actually it is not an integer, but under our assumption, we'll be able to show that this number is an integer. So this number equals square root of -1 squared times k squared. We need to show that this number is an integer. Actually, it is not an integer because square root of 2 is irrational. This one cannot be an integer. But under our assumption that square root of 2 is rational, then this one becomes an integer. Okay. So in order to do that, we change the form. This one becomes 2 plus 1 minus 2 square root of 2. Okay. So that's what. So that one can be rewritten as 1 plus 2, 1 minus square root of 2. Right? So rewrite it, it's become 1 minus square root of 2 minus 1. Okay? So this one is equal to this one, k squared. Okay, so that's algebra manipulation here. So we change the form, we're rewriting this way. So that becomes k star minus 2 . So this number equals this number. All right, so what we have here, k star integer. This one, by our assumption, it's a positive integer, it's an integer. So we have integer here. Actually, this one less than 0.5 k star. So 2 times this one is still less than. So k star, the whole number will be still positive. Okay. All right. So integer here. So what we get is we know this one is integer, actually positive integer. So eventually, what we get is we showed there are a smaller k here, smaller number k prime. So k prime equals this one, namely k prime equals this one. It's less than middle, it's about the middle point, okay? 0.4 something. So take this number, then we get square root of 2 minus 1 times k prime give us an integer. So that means k prime is in the set k. But this causes contradiction because we knew that this one is the smallest. We do not have anything on this side. But now we find the small one. And the assumption that square root of 2 is rational, then we find the one here. So this contradicts to our assumption that this one is smallest because this one is smaller. So therefore, it's impossible. Set k must be empty. Set k must be empty. So that means the assumption that k is rational, square root of 2 is irrational, cannot hold, because hold just give us contradiction. So because this, we know that our original assumption, square root of 2 is rational, is wrong. So the only way is that square root of 2 is irrational. Okay. So here is a different example to use well-ordering principle to prove things. This one is subtle. So it's very difficult to come with this proof by yourself. All right. So roadmap is assuming this one is rational. So then we'll have construct a set k such that we have a smallest element k star. Then we'll obtain a smaller one. This is called a contradiction. We get a smaller one. This is called a contradiction. All right. Okay. All right. Actually, no, I'm running out. Okay, so I will maybe delay to next week to talk about natural numbers and the mathematical induction. Actually, you see that when we prove this, not this was the previous example. Actually, you see it's basically the same as the mathematical induction, but that's the other way around. Okay, so the point of view is different. Mathematical induction, we just from n to n minus n plus 1 goes this way. But for well-ordered principle, actually we from n to n minus 1 in this way. So mathematically index n minus 1 to n in this way. Here n to n minus 1 in this way. But actually improving this, rather it's twisted again. So in order to do that, one way is to use n1 is true, n minus 1 choose, and n is true. But then it becomes same as mathematical induction. So these things really actually it's the same thing, but just different ways of looking at the thing, different way to express things. Okay. All right. So I think I will stop here, and you can enjoy your long holiday weekend for 4 days. Okay. I will post information on how to submitting homeworks today. Okay, it will be online submission. I haven't finished that part yet. I will get it done so you can submit online after the holidays. Okay. All right. Okay, that's it. Thank you.